Okay, so it's a pleasure to have Alexandru Aleman speaking to us from Lund. And the title of his talk is Backward Shift and Nearly Invariant Subspaces of Fock-type spaces. Alexandru.
Thank you so much, Marco. And I'm so happy to see that you guys are doing well under these circumstances. And thanks for the invitation. I have a little spot here. Should I close this? Do you see the whole picture?
If you can close the little square, I think it will be better. Yes, thank you.
All right.
That is good.
Okay, so let's go. Good. So here I want to explain what first what kind of subspaces I mean, even if you're probably used to them. So usually when we have a Banach space of analytic functions in a given domain in one variable, we say that the closed subspace is nearly invariant if you can divide out zeros. So whenever you have a function with a zero, which is not a common zero of the whole subspace, you can divide it out. And you stay in this subspace. Now, a more restrictive thing is if you ask that this divided difference stays in the subspace. And then we say that the subspace is backward shift invariant in this case. All right, so this near invariance is a term coined by Saracen. This was the time when Royden and Heath described all invariant subspaces of multiplication by z in an annulus. And it involved nearly invariant subspaces of the Hardy space H2. This was a nice time. So in any case, Saracen started with that. And there is a structure theorem for these objects, which is quite interesting. So it's still, part of it is a little bit mysterious, but anyway, this is not quite the setup where I want to continue. Yeah, I mentioned that it's a good exercise for a student. If you say that the near invariance condition is sufficient to hold in one point, because then you show that the set of these points is closed and open in the domain. Okay, and as I said, backward shift invariant is a more restrictive notion, and the most known example are the model spaces, right? When you are in H2, when the space, underlying space is the Hardy space, and then they are called model spaces because this comes from Cauchy-Knox theorem about models for strict fractions. Okay, now.
Jose has a question.
Yeah.
Jose has raised a question. Please, Jose. Or maybe not.
Great, it's fine. It's fine.
Yeah.
Are you good?
Yeah, it's okay. It's okay.
Okay.
So,
okay. Now this near invariance, you meet it all over the place when you do analysis in one complex variable, because this dividing zeros is a basic property. In several variables we don't have that, or much more difficult if we can do anything. But here's an example when you study symmetric operators, like Schrödinger operators. And let's say you have indices 1, 1, deficiency indices 1, 1, then you can construct a Hilbert space which consists of analytic functions in the complex plane minus the real axis, or even bigger domain. And this space is itself nearly invariant. And then you obtain a representation of your symmetric operator, a diagonalization, so to say, unitary equivalent to multiplication by the independent variable. And this was done long ago by Mark Crane. I have a long paper on this where Rob Martin and Bill Ross and I, we show how you can do this in an abstract way. Crane used self-adjoint extensions of T, which exist in this case. But now, if you think in terms of Schrödinger or other differential operators, linear, with the indices 1, 1, then this is a quite common technique. I mean, people solve eigenvalue problems and then they establish, with help of those solutions, the T and the MZ. Okay, but now maybe the most important class, I mean, historically speaking, are the branch spaces, right? These are reproducing kernel spaces of entire functions where this flip f bar of z bar is norm preserving, and you can divide out zeros, but not only that, if you multiply with the Blaschke factor determined by the zero, then this is an isometry. I mean, this preserves the norm as well. Now, these are deeply involved in spectral theory, and but one of the most striking theorems, deep theorems of Louis de Branche, which can be found in his book, says that the collection of these nearly invariant subspaces is totally ordered by inclusion, which is amazing. I mean, you know, any two, one of them is bigger than the other is the only possibility. So this is a very deep theorem with wide applications in spectral theory. I met this phenomenon also working on differentiation invariant subspaces of C infinity of an interval. And I started with Boris Korenblum in 2008 to describe those which have where differentiation has the spectrum void. But then I continued with Anton and Jura and to work on them, and they continued about the spectral synthesis. It's a splendid result which they described completely the spectral synthesis in in a certain class of subspaces. Well, basically where differentiation has discrete spectrum. Same type of phenomenon deeply already 12 years ago. But anyway, this is a very important. Yeah.
Alexandru, I think I lost your connection for a few. So after the comment about Anton and Jura's paper, I didn't hear anything else. So the second item, I didn't hear what you said. Can you repeat it, please? Am I the only one having problem with connection?
So I was just saying that I don't know. I wouldn't know what to do, to be honest.
No, please go ahead. I'm just asking if it's me, I'd stop interrupting. That's all.
Okay.
I think there was some problem with connection.
I have problem too.
Okay, so could you please repeat your second bullet?
Yeah, I was saying that this near invariance or nearly invariant subspaces for the standard Fock space are actually involved in the description of Volterra invariant subspaces of H2. This was a method that Boris Korenblum and I developed to describe such objects, Volterra invariant. Okay. Here's the setting for my talk. So I consider we're going to work with spaces of entire functions, and we call them Fock-type spaces because we have weighted LP norms of them. So we take a weight, which we assume to be measurable, positive, and also in addition bounded above and below in any compact. This is not really a restriction, because if you have a weight that gives you space of analytic functions, then you can to be entire functions in the weighted LP space. Here, M2 is, I think I wrote, yeah, the Lebesgue measure on the complex plane. And then if W satisfies these conditions from above, it turns out that this point evaluation functionals are bounded, and then it becomes a closed subspace of L. Of the some examples, the most common are if you take W to be radial weight, so it depends only on the modulus of Z, and of course you assume that this phi, this phi grows faster than the logarithm. Otherwise, you just have polynomials in the space, and it's not very interesting. The standard cases are when you have phi to be a constant multiple of some power of mod Z. So phi of R is A R to the alpha. Okay. If you put P equals 2 and alpha equals 2, then these are the Bargmann-Siegel-Fock spaces. They appear in theoretical physics, in time frequency analysis, in many, many areas of mathematical physics or mathematics. But the non-radial case is quite interesting, and these are quite recent results. So, for example, the branch spaces are also Fock spaces. The weight is not radial, except the only difference is you have to use an equivalent norm to make them Fock space. This was found by Anton Baranov and Dmitry Yakubovich very recently, you see, 2016. Here is the concrete example. If you want the Paley-Wiener, this is the simplest, so to say, the branch space, and the basic. Then it is the Fourier transform of L2 of the same interval. Then the weight you need is the one I wrote here is 1 plus imaginary to the minus 2, e to the minus 2a imaginary. So you can represent them as Fock spaces. Then you have a more general, a notion which was introduced last year by Evgenia Bakubov, Anton, and Yura. And these look like this, except that mu is not necessarily on the reals. It can be also in complex. And the norm is given by the L2 norm. In this case, you can also make them Fock spaces, but with non-radial weight. Okay, now the topic of the talk is these two types of subspaces. The backward shifting invariant subspaces, which should be less in some sense because the condition is more restrictive, and the other one, the nearly invariant subspaces. And these are the two parts of the talk. I'm going to start with the backward shifting invariant subspaces because they are simpler. Of course, if you have such a weight like a radial weight, then you have all the polynomials in your space. And then polynomials of degree less or equal to n, certainly if you perform a divided difference, then you decrease the degree by 1. So this will be invariant for the backward shift, right? So these divided differences in the definition will be polynomials of degree 1 less. Now, if P is 2 and W is really radial, then there are no other backward shift invariant subspaces. All of them must have this form polynomials of degree at most n. This is not direct, it's not simple, but it has been proved. I think this is the father of the Jacobovic. We should ask Anton or Jura, who proved this in 1985. It was originally questioned by Alan Shields, but then it was proved by Jacobovic that weighted shifts with increasing weights have only this very small, totally ordered lattice of invariant subspaces, and translated in our context, this means nothing else than that the backward shift cannot have other subspaces than these PNs, polynomials of degree n. It so happens that if the weight is radial, then you can do the same thing for all P's. Now, as much as I like the proof of this result, it is quite demanding and technically difficult, simply because you don't have a projection. So most of these type of spaces of analytic functions, you have a projection from the big space L2, the weighted L2, onto our space of consisting of analytic functions. But in general, this does not induce a bounded operator for other P's. The projection is unbounded. It's bounded only for P equals 2. Well, if you don't have projection, then you have to analyze the dual, and that turns out to be technical, and I will have to consider to pass. Okay, but here is another theorem which I also like very much, and I can say something about its proof. Suppose you have a Fock space, no matter what weight you have, radial or not, but you know that the space is not very large, so the functions in your space are of finite order. They grow like e to the constant times mod to some power. And this is for the same conclusion holds, namely any non-trivial is Pn. So there are very few of them. And let me just give some ideas how you could prove such a theorem. Well, you have to analyze the annihilator, right? So this means we should know how the functionals look like. Well, since we are in a subspace of LP, weighted LP, they are just given by integration against some function in LQ, where Q is the conjugate index, right? And then if we start with a non-trivial backward shift invariant subspace and take some functional that annihilates it, if the functional is not 0, then it will not annihilate all polynomials. So we can find a monomial, I mean the smallest power, that's what we choose, such that the functional does not kill the z to the n. Okay, and then we write annihilates divided difference of functions. Then we can solve for f of lambda here, right? So we can, since g is in LP, we can take things apart, and we get that f of lambda times this integral equals the other integral with fg. Now, the functions involved here are Cauchy transforms, finite measures in this case. And the thing is that about these Cauchy transforms, we have some knowledge how they behave at infinity. And here is what they do. So if the measure has a number of moments, then you have the Cauchy transform will have a certain behavior at infinity. I mean, the first terms can be determined. The coefficients are the moment, which means that the measure of the intersection with the disk is smaller than the area of the disk when.
Excuse me, Alexandru.
Yeah.
Could you repeat the argument if from the measure with finite moments z, so the integration against zk is finite from there?
Well, I was saying that the Cauchy transform, if it has this finite moments, then the Cauchy transform is you can say what it does at infinity. I mean, you have the first development in the first n+1 terms, and with the appropriate rest. But the problem is that you can only know this in for all lambdas outside of an exceptional set. This set is in some sense small, meaning that its intersection with the disk, its area is much smaller than the area of the disk if the radius goes to infinity. So this is a price you pay. Everything looks very good, but you have to deal with this exceptional set. And now maybe I should go back to this relation. So now I know the development at infinity of this and of this. And if I look at what I got, this one goes like 1 over lambda to a certain power, it would be n+1, and this goes to 0. So this means f cannot beat f of lambda, must be smaller than lambda to the n if you go to infinity. So if we wouldn't have this exceptional set, it would be done, but we do. So the problem is, what do we do with the exceptional set? That is the content of a very beautiful theorem, a version of Liouville's theorem, but but now you need to know that it has finite order. Bound in a complex plane. This theorem is very beautiful. The proof is based on harmonic measure estimates. It's a non-trivial, highly non-trivial theorem, but it's a very powerful result. So this is the way you prove that there are no other backward shift invariant subspaces than polynomials of degree n. Okay, let me just note that there are spaces which do not contain polynomials at all. And in this case, you cannot expect such a theorem. And the example is the pair you see that these subspaces are certainly not ordered, that their intersection is zero. So this depends very much on having polynomials. The assumption that polynomials are dense is important here.
Excuse me, Alexandru, sorry to be a bother. Could you repeat this? I lost you again. Could you repeat this argument when the two subspaces of the Pelley-Wiener space? What are you?
So you start with this Pelley-Wiener minus AA, and
right.
If you take Pelley-Wiener minus A0 and Pelley-Wiener 0A, they are both orthogonal, and their direct sum is the whole space. They are also invariant, so this is a completely different polynomials, and you don't have subspaces which are totally ordered because these are orthogonal to each other. So
okay,
yeah, all right.
Thank you.
Let me go to nearly invariant subspaces. So of course, this is a more complicated structure, and there are many more of them. Definition says you can divide out zeros no matter what. So if you have a zero of a function, you can just divide it out and you stay in the space. Okay, and then here is a simple way of constructing such a thing. Take a function with a given zero set, assume it has only simple zeros, and divide out its zeros into the span and close it. It's a very simple computation to show that you can divide out any zero of any linear combination just from this simple form. The problem is, of course, you should know that this closure, the span is about equal polynomials, but if you take more complicated functions, then a priori we don't know. What we also don't know, this seems to be a quite difficult question, so maybe we don't know if nearly invariant subspaces are all of this form. If I give myself any nearly invariant subspace, is it true that I can find an F to represent it in this form? Or is it call them one generated? I mean, F is basically generated. But at this time, we really don't know about that. Okay. Here's the beautiful result I want to present you, namely that we have an ordering theorem similar to the branch theorem for such spaces. So if we are in a weighted for a Fock-type space, which is small in the sense that, well, the functions, all the functions have zero exponential time. So they grow slower as the e to the mod z. Then the collection of all nearly invariant subspaces is totally give me two. Anton was visiting Lund for a longer time. I mean, he was a visiting professor in Lund, and we were working on a quite difficult problem, again, about differentiation invariant subspaces of C infinity. And then we switched to this subject where we could do something, but The problem is still there, I guess. And Anton was basically the driving force here because, you know, then we could collaborate with Jura as well, who was in St. Petersburg, and then with Håkan. Anton visited him in Stockholm. And this is one beautiful theorem that came out basically merely due to the Anton and Jura. So let me just tell you a word about the proof. I won't talk you through the whole proof, but if you go back to Louis de Branche, the way he proves his ordering theorem is he starts with a very deep result of Maurice Haynes, which says that if you take the minimum of the moduli of two entire functions of zero exponential type, and that's bounded, then one of them must be constant. Now, Haynes' result is actually more general than this, but this is, I hope you believe me that this is a completely non-trivial theorem because with just one of them is Liouville's theorem, but with two is a completely different issue, right, to compute the minimum. Okay, but for our purposes, we need a refinement of this. And here is the beautiful thing that you can do. So you have the same situation, the minimum is bounded, but again, outside an exceptional set. This exceptional set is the condition is more than being planar, what was density 0. But still, it's not very restrictive, I would say. So it's a small set in some sense. And then the conclusion is the same. Either one or the other must be constant. So this is the way it goes. And then we follow, of course, ideas of the branch, but they have to be adapted to the context we're working here. Okay. Let me give you some applications of this ordering here. So first, if you start with the Fock-type space of zero exponential type, so all the functions are zero exponential type, and suppose the polynomials are dense, for example, if the weight is real, then you cannot have any other nearly invariant subspace than the polynomials of degree less or equal to n, because if you have the polynomials, then the pn's are certainly nearly invariant. But then you cannot have anything else because they're supposed to be totally ordered. So whatever other subspace you take, and if you compare it with a Pn, either it contains it or it's contained in P. What is contained in Pn is certainly some other Pk, and if it contains all the Pn's, then it contains all the polynomials and it's trivial. So this is a very simple consequence. Then here's another type of result about these one-generated subspaces. So you start again with such a Fock-type space of zero exponential type containing polynomials that then subset. And then take a transcendental entire function, right, with simple zeros, and do this span. Well, I hope it's clear that this has nothing to do with polynomials, but it will be nearly invariant if you close it. Yet, it has nothing to do with polynomials, but then it must be the whole space. Again, because of the ordering theorem. So any transcendental function, if you divide it zeros, do the span, and you can approximate any function in the space that way. Okay. If we don't have zero exponential type, then the theorem fails, and the threshold are this weights e to the minus a mod z to the alpha for alpha greater or equal to 1. And the reason is very simple, because Now you can multiply polynomials with exponentials. And you get a nearly invariant subspace, obviously, because if you just multiply with the function, nothing happens. These are finite dimensional, right? And there's no way to order them. They cannot be totally ordered. So this means the theorem cannot be true. But then, of course, the natural question is, can we find infinite dimensional spaces? But this requires work. It requires work. And this is not for free. So the few minutes that I still have, I want to discuss a few examples of infinite dimensional nearly invariant subspaces here. How we can produce them. I mean, we have several methods to do that. And the one I wanted to present tonight is based on the use of the fragment-Lindelof principle. This is a neat idea. For me, fragment-Lindelof is somehow spectacular theorem. I know it's pretty much the maximum principle, but the consequences are sometimes quite spectacular. And maybe, I don't know how spectacular mine is, but you'll see. Okay, so we start with the limit case. See, the power e to the minus mod z, so alpha is 1. This is the weight, and estimate the norm of the point evaluations. So the functions in this space will grow like, remember the p is 2. So it's like constant, absolute constant, e to the mod z half, norm f. And then we come with the following. We consider the functions which grow like, whose growth is somehow dominated by this exponential of the real part of z half plus mod z to the 1 half. Let me say a word about this. So when you are in an angle, or let's say on the positive real axis, then the growth is the same as this, right? Because this mod z to the 1 half is not going to influence that. But if you now go on the negative axis, then this becomes negative. It will beat this mod z to the 1 half, and you basically go to 0. And you realize that in angles is a similar, instead of going on the axis, you can take angles. So what's about this subspace? Well, it's certainly infinite dimensional because you can take e to the z half times any polynomial, because this mod z to the 1 half will be okay. And that gives you infinite dimension. If you want to test the definition of near invariance, that's pretty easy as well. I mean, this is just a growth restriction. If you divide by z minus lambda, nothing going to change except this constant, cf, maybe. But what is not clear at this point is whether we created a closed subspace, because it's not closed, then this is not interesting, right? Well, this closed, I'll look at it again. The problem is this constant f, right? So suppose, depending on f, suppose you have a sequence fn, which converges in the norm, but then the norm will only give you this type of growth. It could be that the CFs explode and you lost this condition, right? This is, I would say, reasonable to think. But it's not so because of fragment-Lindelof. You just form this function, so you replace z by z squared, and then multiply by e to the I z. Well, then you look at this only in the upper half plane, right? Because and here's what you have in the upper half plane. So on the real line, this G obeys the restriction that the function that comes from the estimate of the point evaluation. But on the imaginary axis, the best estimate is this C, which depends on the F we started with. So G comes from an F, right? So that's where CF comes. And in the whole half plane, you have something like this with e to the 2z. And now here is a trick, which actually Håkan was very good with that, and he suggested. So you divide the upper half plane in two quadrants, right? The positive real part, the negative real part, and apply a fragment Lindelof, right? So then on the sides of each angle of pi half, you have the function is bounded, it is continuous in the whole thing, and inside you have such an estimate. And that's enough for an angle of size pi half to apply fragment Lindelof, and you get, you conclude that this is bound. Well, if it's bounded in each of the quadrants, being analytic in the whole half plane, of course it will be bounded in the whole upper half plane. But then the supremum is computed on the real line, right? Because these are Poisson integrals now. So here you have the right estimate. Is A is independent of F. It's only the norm of F which appears there. Well, that's exactly what we needed. Right? So here is the estimate for G rewritten, and here is the estimate for F in M. So I replace the CF with A times norm F, and then the fact that M is closed is immediate. Fine. Now, this technique, I mean, this is a very simple example that I showed to you, but you can do this in a much more general context. So you can work with angles of any aperture. You can work with several angles. Of course, the thing becomes a little more sophisticated, but in this idea of using the fragment Lindelof principle is what's behind. And the rest is, I would say, more technique. And you can get a number of interesting examples of nearly invariant subspaces which are infinite dimensional if you have this larger group. I should say that, see, this type of estimates that we impose to create such subspaces are in angles. Now, you could have estimates, you could define conditions which are just on a line, but then these are no longer growth conditions. So if you're on a line and you want to construct something like this, you should somehow impose conditions that the restriction, the function of the line on the line belongs to some Hardy, or let's say a Paley-Wiener space. Then you can construct such examples as well. And now, one topic that I like very much, but I don't have the time to get into it, is you can construct also such one-generated subspaces. Now, this is technically, again, more demanding, but it is quite interesting that you can construct such subspaces. So, for example, in the Siegel-Bargmann space, in the standard one, you use this Weierstrass sigma function to, yeah, no, sorry, let me go over this because it's a little bit too technical. I don't want to stay too far from the truth here. Okay. So a common feature of these examples that we construct of infinite dimensional nearly invariant subspaces is the fact that these functions in such subspaces have a very asymmetric behavior. I mean, if you look back at what I had with my M here, where is it? Ah, here. So you see that this function behaves very asymmetrically. So it's allowed to grow in any angle, well, let's say on the positive real axis, but on the negative real axis, it behaves completely different, right? It has to go to 0. And this is common to all the examples we have. So we asked ourselves, what's happening if there's some symmetry here? What's going to happen? And well, what happens is you cannot construct examples anymore because if you impose symmetry conditions, well, let's think of a rotation. So compose with the rotation and ask the nearly invariant subspace to be invariant also for the composition with this rotation. And then these subspaces automatically don't exist anymore, and you're confined to the PNs, polynomial degree less or equal to n. What's even more surprising, this is happening also when beta is the angle of rotation here. When this beta is just a rational multiple of 2 pi, well, if the underlying space is not too large, then you can prove that there is nothing there except the PNs. If beta is not a rational multiple of 2 pi, then you always get only the polynomials of degree n. If not, you have to impose a condition for this. Well, thank you very much. And it was great seeing you.
Thank you. Are there any questions? Well, I'll start with one then we'll see the others. Alexandru, just about your last comment about lack of symmetry. But what happens if you take the subspace that you just constructed with the growth on the positive x-axis and the decreasing on the other x, and you take minus that space? So you make it symmetric in the sense that they take the subspace that grows on the negative x-axis and goes to 0 on the positive x-axis, and you take the sum. Don't you get something?
That might be dense. I'm not sure, but
so it could be the sort of the complement. Okay.
It could be
the sum of the space.
Could be dense, but I don't have a proof right now. But it could happen. One has to check. If it's not dense, then wait a minute. That one will be rotation invariant, right?
No, why? Because you've rotated by pi, but not if you because along the so you would be just rotation invariant. You just being by one angle.
I want one angle, not all. So rotation by pi, but we have
no, yeah. That my example would be invariant by rotation 1 by pi.
But it's still, I mean, in that last thing we have a condition. I mean, these functions. Let's say we were in the weight was e to the minus mod z, so we wanted somehow these functions to be of type 0 with respect to this order. So maybe there is something. I'm not sure. I have to look at it. Yeah. But in general, the theorem is about one rotation, no matter.
Okay.
So if it's irrational, then of course you can iterate it, and you have many rotations. But if it's rational, then it's unexpected. You would say, well, why can I do that? My guess is you cannot do it. You get the whole space.
Okay.
Yeah.
Thank you. Are there any other questions or comments? Well, then I'll ask another question myself.
Okay.
So the space of functions of zero exponential type seems to play a very peculiar role here, and I mean, it's anyway. It's a stupid remark, but it's just because of Crane's theorem. No, it's not Crane's theorems. The one about the branch, the minimum. If the minimum of the two functions is
yes, certainly that's not going to work. It's heavily involved there. Yeah, I mean the Haynes theorem also assumes that the functions are of zero exponential type. So that is. Without that assumption, this is not going to work. So even the standard Haynes theorem needs that zero exponential.
Yeah, no, I mean, I find it very peculiar theorem. I'm always, all the time that I look at it, I find it extremely puzzling for the conclusion that it gives. But
there is, I don't know if Anton or you are here, because there is some progress in this direction. So now I forgot the names, but there are very recent, there is recent work on this Haynes theorem and extensions of it, which are quite interesting. But now I forgot the name. I have the paper sent by Anton. Anton, are you here? Nope. Yura.
Yes, I am here, Alexandru. Yes, I think you mean the paper by Alexei Kulikov.
Oh, yeah.
Exactly.
Student of Yura, yes.
Yeah.
Obtained very interesting, nice results about this Haynes theorems and very interesting refinements.
Yeah.
Yes, he goes much deeper into this.
Yeah.
I mean, that's Kulikov. Now I remember. Yura is your student, right?
Yes.
Okay. But it's very nice work. Yeah.
okay. Are there any other questions? Well, if not, we thank Alexandru again.
I thank you for the invitation. And can I use this link